This video is on solving exponential equations. Now, exponential equations are basically indices and applying the rules of indices to solving equations. And they're generally solving equations where the unknown or the variable is in the exponent. So we're going to be working largely with the rules of indices, and these are the rules of indices as they appear in the log tables on page 21. So have the log tables open next to you as well, so that you know what we're referring to. So before we get stuck in properly, let's look at a little bit of vocab first so that we know what we're talking about. So say, for example, we have a term like 2 to the power of 3. The two parts of this term, the 2 and the 3, they have two different names. The 2, which is the number written here, the large number, is called the base. And the 3, the number written up at the top here, is called the exponent or the power or the index. And when we want to work with the rules of indices or the rules of exponents, it's really quite important that we try and make sure that the bases for all our terms in an equation are the same. And that's going to be our initial job in most of the questions that follow. So let's start off with a nice simple example. So this question asks us to solve for x. We can see that the x, the variable, is in the exponent. So we're going to be, first of all, looking to try and get the same base throughout our equation. Okay, so looking at the 4 and the 32, what base might work well for both of these? Well, I can't stick with 4 because if I look at 32, I can't write 32 as a power of 4 because 4 to the power of 1 is 4, 4 to the power of 2 is 16, 4 to the power of 3 is 64. I've bypassed the 32 completely. So I need to find a common factor for 4 and 32 that I can use as my base. And the obvious choice here is 2 because 4 is obviously 2 squared. And 32 is also a power of 2. Let's deal with the 4 first. So I can replace 4 with 2 squared, but I mustn't forget about the x. So the x goes in outside the bracket. And next I need to figure out what 32 could be. So 2 to what power? Now I can go to my calculator and I can type in 2 to the power of 1, 2 to the power of 2, 2 to the power of 3, and so on, and see what brings me up as far as 32. Or I can just multiply 2's together and then count how many 2's it takes multiplying to get up as far as 32. Or I can start with 32 and I can divide by 2 and see how many times I have to divide to get down as far as 1. Any of these approaches will work. We'll find that 32 is 2 to the power of 5, so I'll replace 32 with that in the equation. Okay, so now I've got the same base throughout my equation. That's really important to be able to solve an exponential equation. But I also need to have just one simple term on each side of my equation, because that then will allow me to get rid of my bases completely and just work using my exponents or indices. So I have to look at my equation and see, are there any of the rules of indices that I can apply at this stage? So I see, for example, that I've got 2 squared to the power of x. So looking down through my rules here, do any of those rules look like they might be the appropriate one to apply? So you can see pretty obviously it's going to be rule 3, a to the power of p to the power of q is a to the power of pq. The bracket helps us to remember that we should multiply. So here we're going to change this term so that it reads 2 to the power of 2x. And the 2 to the power of the 5 doesn't need to change. Okay, so now I've got one term each side. The base is the same in both cases. It's 2 in both cases. So now what I can do is I can just get rid of the bases and just solve using the powers. Just bear in mind that I can only do this if I have one term each side, if the base is the same, and if I've already applied any rules that needed applying, like say, for example, here I needed to multiply my powers. Okay, so I'm now working with 2x equals to 5, and this is pretty simple to solve. X equals 5 over 2. Obviously 5 over 2 can be written as 2.5 or 2.5, but I would encourage you when you're dealing with exponential equations, particularly if you're solving for a power, when you get the answer, to leave it as an improper fraction if that's the way that it turns out. So 5 over 2 is fine. And I'm just going to take a moment to kind of do a little aside to explain why this is a nice way to write your answer down for a variable that's in an exponent. So to do so, I'm going to go back and look at the original statement in the equation. 4 to the power of x equals 32. So if I now know what x is, it's 5 over 2. I'm going to put that in, okay? So I can say 4 to the power of 5 over 2 equals 32. Now, what this shows me that would be lost if I was to write down 4 to the power of 2.5 or 4 to the power of 2.5 is actually how I get from the left-hand side of the equation to the right-hand side of the equation. So when I've got a fraction power, what's really going on is that the top part of the fraction is just a regular power, so like a power of 5 in this case, and the bottom part of the fraction is a root. So what this is really telling me is it's a set of instructions. It's saying get the square root of 4 and then put that to the power of 5, and that gives you 32. So let's actually just check and see if that set of instructions gets me where I want to go. So like I said, this is the root. So I'm rooting 4 and putting my answer to the power of 5. Okay, well, what's the root of 4? The root of 4 is 2. So now I've got 2 to the power of 5. And when I work out 2 to the power of 5, that comes out as 32. And that's why it's nice to leave your answer for an exponent in improper fraction form, if that's how it turns out. One other thing to note is that the order in which you apply your root and your power doesn't actually matter. So I could put the 4 to the power of 5 first and then square root. So applying the power of 5 to the 4 first will get me the root of 1024, and the root of 1024 comes out as 32. Okay, I'm after getting slightly sidetracked here just to point out this here, the x equals 5 over 2 is the answer for my example. This is just a little bit of a side note on why improper fraction powers are better than decimal versions or mixed numbers. Okay, so here's example 2. Again, I've got my log tables next to me so I can refer to them. Okay, so example 2 asks me again to solve for x. Again, we can see that x is up here in the power, so we've got an exponential equation. It's 8 to the power of x equals 1 over 16. Now, so like we said before, we want to get, if possible, one term on each side with the same base and apply any rules, and then we'll be able to just deal with the powers to solve out for our x at the end. So the first thing to have a look at is, do we see any potential bases? So looking at 8 and 16, I want to think about a common factor, and particularly a factor that I can use to write with a power. So, okay, 4 is a common factor, but that's no good because I can't say 4 squared is 8. That would give me 16, all right, but it would bypass the 8. So I need to think smaller. So 2 is going to be my base again in this case. So I'll replace the 8 and I'll replace the 16 with terms that have 2 as the base instead. So starting with 8, 8 is 2 to the power of 3. So I'll say 2 to the power of 3 for the 8, all to the power of x. And it's important to put that bracket in there. And then I want to replace the 16 as well. And I can write that as 1 over 2 to the power of 4. So now I need to apply any of the rules that I can from my log tables from page 21. And looking at my first term here, first of all, on the left-hand side of the equation, power to a power, again, that's rule 3 that I need to apply. So I'm going to end up with 2 to the power of 3x. Okay, so now what about 1 over 2 to the power of 4? Again, I'll go to my log tables and I'll see does anything jump out at me. Don't forget, don't just look at the left-hand side of the rules. Have a look at the right-hand side of the rules too, because sometimes the information you need isn't there. So I've got 1 over 2 to the power of 4. So which rule do you think is applicable? So it's rule 5, because if you look at the right-hand side of rule 5, it's 1 over a to the power of p. That can be written as a to the power of minus p. In this case, that's going to be 2 to the power of minus 4. Okay, so now I've achieved my first goal, which is to get the same base and one term on each side with all the rules applied. At this point then, I can cross off the bases and work with just the exponents. And it's pretty simple to solve this. 3x equals minus 4, x equals minus 4 over 3. And like before, leave it as the improper fraction. Don't go changing it into anything else. Okay, so example 3 is a slightly longer example then. We're still solving for x, but there's a bit more going on in the equation. We're still aiming for the same thing. We want one term each side of the equal sign. We want the same base. We want all the rules applied. Then we can cross the bases off and work with just the exponents. So I first of all looked through the numbers in the questions. I've got 9 and 3 and 27. So what might be a potential base for all of these? Well, 3 goes into all of them. And in fact, 9 can be replaced with 3 squared and 27 can be replaced with 3 cubed. So I'm going to first of all start by doing that. So on the left-hand side, I've got 3 squared to the power of x. Now on the right-hand side, I've got 3 terms. I've got the 3, I've got the root 3, and I have to take that root into account, and I've got a root 27 on the bottom. I'm going to start off by just looking at the top of this particular term. So 3, I'm going to write as 3 to the power of 1. At this stage, everything that is a base needs to have a power so that I can use the rules of indices to proceed through the question. Now I've got the root 3. Okay, so when I've got a root, I want to use a fraction power. So you can see here, for example, q root a is a to the power of 1 over q. Now, I don't have any little number written into the hook of this particular root. That's because it's a square root. I could put a little 2 into the hook if I wanted to, but we tend not to. We assume it's the square root. The square root is always going to be given by a power of a half. So I'm going to replace root 3 with 3 to the power of a half. On the bottom, I've got root 27. There's a few steps that I have to go through here. I can do them one by one, or I can do them in the same stage if I like. First of all, I'm looking at the 27. So 27, I want to write it as a power of 3. So 27 is 3 to the power of 3. But I mustn't forget that my denominator here is not just 27, it is root 27. So I've got 3 to the power of 3, but the root also acts as a power. It's a power of a half. Okay, so I've got a bit to do now here still. On the left-hand side, I've got a power to a power. We'll recognise that as being rule 3. We've done that a few times already in this video. So I'm going to rewrite this as 3 to the power of 2x. Okay, so now to the right-hand side of the equation. Okay, I'm going to deal with the numerator first of all. So I've got two terms here, 3 to the power of 1 and 3 to the power of a half, and I want to multiply those together. So looking down through my rules from the log tables from page 21, which rule is applicable here, do you think? So it's the first rule. I'm multiplying two terms together and I'm going to add their powers. So 1 plus a half is 1.5, or 3 over 2 if you prefer. And then on the bottom, I've got a power to a power, and I must multiply these together. So I'm also going to get 3 to the power of 3 over 2 there. Okay, now I have got terms that are dividing. So I look to my rules from the log tables, and I see that division means that I subtract my powers. So I'm going to have 3 to the 2x on the left-hand side still, and then on the right-hand side, I'm going to have 3 to the power of 3 over 2 from the top, minus the 3 over 2 from the bottom. And of course, that's going to give me 0. Okay, so now I've got one term each side. They both have the same base. All the rules have been applied. I can cancel out the bases and work with just the exponents. So 2x equals to 0. So I'll divide by 2, and I get a result in this case of x equals to 0. It's interesting to look back to the beginning of the question here and think what would happen if x was 0. What's 9 to the power of 0? Well, anything to the power of 0, we can actually see it over here on the right-hand side in rule 4, is 1. So the left-hand side is 1, so that means 3 root 3 over root 27 must work out as 1. And if you go to your calculator and type this in, you'll see that when you evaluate it, you do get an answer of 1. So the solution for this, x equals 0, is happening for that reason. Here we have example 4. There's a bit more involved in example 4. You can see, for example, that I've got more than two terms. That might not be a problem in itself, but I can see that I've got addition and subtraction between the terms, and there aren't any rules in the log tables, in our rules of indices, for adding and subtracting the bases. It's only rules that apply to the powers. So we need to find a different way of going about this. In a question like this, we need to use substitution. And in many cases, actually the middle term, as long as it's arranged in this order, the middle term may give us a clue as to what the substitution should be. So I'm actually going to take 3 to the power of x and call it something else. So I'm going to say let y equal 3 to the power of x. Okay, so let's see where that's going to get us. So obviously it'll let me replace this 3 to the x with y. It won't let me do anything to the 3 at the end. But what will happen with this first term here? Notice that this first term is 3 to the power of 2x. But I've only got something to substitute in for 3 to the power of x. So I have to try and take this term first of all and kind of isolate the 3 to the power of x part of it. So to do that, I'm going to go to my log tables again, and I'm actually going to have a look at rule 3 once more. So I want to get 3 to the power of x, and the powers are multiplying together, the 2 and the x, so I can split them up like I see in rule 3. So instead of writing it as 3 to the power of 2x, I can write it as 3 to the power of x squared. Notice that 2 by x would give me back that 2x there in the first line. So now that I've identified a couple of different places where I can see 3 to the power of x, I'm going to replace those 3 to the power of x's with y. So now I have something that I recognise. This is actually a quadratic equation. So I'm going to factorise and solve for y. So pause the video for a moment while you do that, and then play and see if you have it correct. So I get y minus 3 times y minus 1 equals 0. So I allow each factor to be equal to 0.